Welcome to our lecture on Riemann integration. Today we are going to explore the fundamental theorems of calculus. These theorems are arguably the most important discoveries in the history of mathematics, as they connect two seemingly opposite ideas, measuring how fast something changes and accumulating those tiny changes to find a total amount. Let us start by thinking about a simple car journey on a long highway. If you look at your speedometer, you know your exact speed at any given moment. If you keep track of that speed over time, you can easily figure out the total distance you have traveled. Conversely, if you know your exact mile marker at every single second, you can calculate your speed by seeing how fast your position is changing. Differentiation measures this instantaneous rate of change, while integration accumulates those tiny changes to find a total amount. The fundamental theorems of calculus prove that these two everyday concepts are exact mathematical opposites. Now that we understand the basic relationship, let us look at the first fundamental theorem of calculus. This theorem establishes the formal link between an area and a rate of change. Imagine a smooth, unbroken curve. If we define a new function that represents the accumulated area under this curve up to a moving endpoint, the theorem states something remarkable. The rate at which this area grows is exactly equal to the height of the boundary that is adding the new area. To visualize what we just discussed, look at this graph. The horizontal axis represents our variable t, and the curve is our function f of t. The light blue shaded region is our area function, f of x, accumulating area from a fixed starting point a up to a moving point x. When we move a tiny step forward by a distance h, we add a thin dark blue slice of new area. The height of this new slice is exactly the height of our function at x. This visual intuition leads us directly to the mathematical formula for the first fundamental theorem. Conceptually, it tells us that taking the derivative of an integral simply returns the original function, stripping away the integration. In this equation, f prime of x represents the instantaneous rate of change of our accumulated area. The term f of x is the height of the curve at that exact moving boundary. If the height of the curve increases, the area accumulates much faster. If the height drops to zero, the area stops growing. This beautifully proves that integration and differentiation are inverse operations. Before we prove why this works, let us see this theorem in action with a concrete example. We are asked to find the derivative of an area function defined by the integral of sine of t squared. Integrating this manually is notoriously difficult, if not impossible for us right now. But why struggle? By applying the first fundamental theorem, we bypass the integration entirely. We simply take the upper boundary variable x and plug it directly into the inside function. The final answer is simply sine of x squared. The theorem turns an impossible problem into a trivial substitution. Now that we have used this formula to solve a problem, let us understand where it comes from by proving it step by step. We start with the standard definition of a derivative applied to our area function. The numerator represents the difference between the slightly larger area after taking a small step forward and the original area. This difference is just the area of that tiny new slice we saw in the diagram earlier. We can rewrite this exact strip mathematically as a definite integral from x to x plus h. This sets up our rate of change perfectly and prepares us to evaluate the limit. Continuing with our derivation, we need to evaluate that tiny integral we just set up. Because the curve is continuous and unbroken, as the step size h shrinks to 0, we can approximate the area of this tiny vertical strip as a simple rectangle. The height of this rectangle is approximately f of x, and the width is our small step h. We substitute this rectangular area back into our derivative fraction. The width h completely cancels out from the top and bottom. This leaves us with the final beautiful result. The derivative of the area function is exactly the height of the function itself. So, we have proven that the first theorem holds. This brings us to the second fundamental theorem of calculus, which is the tool you will use most often in practical problems. While the first theorem gives us a conceptual link, the second theorem provides a direct, practical method for calculating the exact numerical area under a curve between two fixed points. It tells us that the total accumulation of a quantity is simply the difference between its final state and its initial state, calculated using an antiderivative. This concept translates into a very powerful and widely used formula. To evaluate a definite integral from a to b, you first find the antiderivative, denoted by capital F. This is a parent function whose derivative gives you back the original curve. Once you have this parent function, you simply plug in the upper boundary b, plug in the lower boundary a, and subtract the two results. If the upper boundary increases, the total accumulated area grows. If the boundaries are the same, the area is 0. This formula completely bypasses the need for exhausting geometric approximations. Let us apply this second theorem to a classic geometry problem. We want to find the exact area trapped under the curved parabola 3x squared between the vertical lines x equals 1 and x equals 3. Instead of drawing infinite tiny rectangles, we use a new shortcut. Our first step is to find the antiderivative of the parabola's equation. We ask ourselves what function, when differentiated, gives 3x squared? Using the reverse power rule, we find that the parent function is simply x cubed. Continuing with our calculation, we now apply the core rule of the second fundamental theorem. We take our parent function, x cubed, and plug in the upper boundary of 3. Then we plug in the lower boundary of 1. We subtract the starting value from the ending value to find the exact amount of area added between those points. 3 cubed is 27 and 1 cubed is 1. Subtracting them gives us a final answer of 26 square units. What would have taken pages of complex limit calculations is solved in 3 simple lines. Now that we have seen how incredibly useful this shortcut is for calculating areas, let us prove why it works by building directly on our first theorem. We start by defining a specific area function, g of x, that accumulates area starting from our lower boundary a. By the first theorem, we already know that g is an official antiderivative of our curve. Now, suppose you found some other antiderivative, f of x, using standard calculus rules. Because both functions have the exact same derivative, they must be identical, except for a possible vertical shift, represented by an unknown constant c. To finish our proof, we need to figure out exactly what this unknown constant c is. We evaluate both functions at the starting boundary a. The true area function g, evaluated at a, is exactly 0, because an area with no width has 0 size. This immediately reveals that the constant c is exactly equal to f of a. Finally, we evaluate the functions at the upper boundary b to find the total accumulated area. Substituting our constant back into the equation and rearranging the terms gives us the final result. The definite integral is simply f of b minus f of a. Let us summarize what we have learned today. The fundamental theorems of calculus prove that integration and differentiation are two sides of the same coin. The first theorem shows that the derivative of an accumulated area is just the original boundary curve. The second theorem uses this fact to give us a practical shortcut for calculating exact areas by simply subtracting the values of an antiderivative. Together, they transform calculus from a theoretical geometry puzzle into a powerful, everyday computational tool. You now have the foundation to tackle complex problems in physics and engineering.